Great. I'm getting hungry. Right. Small lunch. I think I'll need to. No, I still have to teach you, even if I am hungry. I'll be strong. Right. Next lesson. So, we've been doing some very hard lessons lately. So we actually have a little bit of a break and have an easy lesson to look at now. A picture lesson. Lots of pictures in it. So this will relax your brains a little bit. Conservation of energy. Write this down, please. Right, Bruce. Got that? Conservation of energy? Yeah. Now, what does the word conservation mean? Save. Yes. That's what you might say in an EAP class. But it also has another meaning too. So in EAP class you might say conservation of the planet or something. Save the planet. But it has another meaning as well. It's not too different to save, but something else. Maintain. Yeah. So what could it mean to say maintain the energy?
Everywhere.
Yes.
Energy is the same.
Yeah. Close enough. The energy stays the same. That the values don't change. We'll get to that in a moment. Okay, so what is energy? Before we even start with conservation of energy and conservation, first we need energy. So what exactly is energy? Who knows? Yes? You do know?
I can explain this.
Do you want to explain in Korean? I can listen.
Okay.
No, actually, sorry. I forgot. I don't speak Korean. So, anybody can give it to me? Energy? You're close. You're close. You're halfway there. I need another key word in that.
Potential.
Closer. Not quite this word. Another word like this. Oh, now we're moving away. Not quite this.
Oh my.
You see, he said to do work, and then he said potential. So they're both close, but there's a word I'm not hearing, which we need, which is like potential. A. A-B. No? So energy is having energy means having the ability to do work. Yeah. Well, you were close when you said potential to do work.
My thing is, yeah.
I know that's what you meant, but I needed the right word. So it's the ability to do work. If you have the ability to do work, then you have energy. So if something has energy or is energy, what do we mean? In physics, something has or is energy if it has the ability to do work. Okay, so everybody needs to write that down because nobody got it quite right. Got that? So because we've talked about work and energy as an ability to do work, then thinking about the last lesson, what are the units we could use to measure energy? Joules or Newton meters. But joules is fine. Yeah. Okay. So it's also measured in joules. No work, no energy, no energy, no work. So if it can't do work, it has no energy, or if it has no energy, it can't do work. Simple as that. But usually what we have is the work done is less than or equal to the energy. So just because something does work doesn't mean it uses up all its energy to do the work. So as I'm doing work, I still have energy left to do more work. But it's important that you understand that the work done is less than or equal to the energy. It'd be quite odd if the work done was more than the energy available to do the work. I mean, that would be quite impossible. You know, if I can do 10 joules of work and then I manage to do 20, well, something strange happened. Yeah. So usually what we do in most physics problems is we say that, you know, if I have 1 megajoule of energy, then I can do up to 1 megajoule of work. Often for the problems we look at, all the energy is used up doing work. So often we find that the work equals the energy. Usually we say that the work done equals the energy it had, and it used up all the energy to do the work. So often when people say work, they sometimes mean energy, but we can kind of switch the two. And that's fine, as long as you remember, really the energy could be bigger than the work. But if you say all the energy went into the work, then you can nearly swap the words. So sometimes I say work, sometimes I say energy, often they're the same. But if we want to be careful, we should remember that energy can be bigger than the work. Yeah? But don't worry too much about that. That's not a big deal. It's just an English issue. So there are many types of energy. That is, there are many types of things that can do work. Get ready. Let's have a look at all the different types now. Okay? So there's different types of energy, meaning that there's different things that can do work. So what are some of those things? So of course this is not everything, but it's the important ones. So the first one is electrical energy. So if you can write this down, the first type of energy, electrical energy. I think it's clear from the picture what I mean. This is an important type of energy because when you think about your day-to-day life, most of the work done in your day-to-day life is done from the electrical energy, the ability that this has to do work. Okay, so you know, it can power the laptop, power the projector, you know, microwave, kettle, dishwasher, everything in your home. Electrical energy. So a very, very important type of energy. You wrote that down? Electrical energy? Yeah. The next type of energy. Magnetic energy. So these magnets have the ability to do work. In this example, what work is the magnet doing? It's, well, simply what it's doing. It's lifting the metal. So what's the force? It's an upward force, pulling it up. And what's the distance? Between the ground and how far it moved it, it's this distance here. So the second type of energy is magnetic energy. So this magnet has the ability to do work, and the work it can do is apply a force to lift up metal. Yeah? Okay, did you write that down? Magnetic energy. Yeah? Okay. Next type of energy. Most delicious kind of energy is chemical energy. Like, I mean, I don't know, have you ever tasted electrical energy? It's doesn't taste as nice as this. I have not done this, but Lorraine has. You can ask her what it tastes like. You can take a battery and stick it on your tongue. You can ask her what it tastes like. Has anyone done this before? No.
You can try it.
Have you done this? I see, we have one person now. Do you remember what it tastes like? Sour? Sand. Interesting. I'll take your word for it. I won't test it. Anybody? No? No? Okay. Yeah. Take a square battery. Was it a square battery? Yeah, and just on your tongue. Well, her experience was sand. Yeah. No, I can't. You see, I don't know. I've never done this, so.
Why you don't make video?
Huh?
Why you don't make video?
Actually, that would be a good video for my YouTube channel, wouldn't it? Tasting electrical energy.
We'll make it.
Yeah, yeah. But I get lots of likes on it. Yeah. Do you know what? I'll bring a battery in next time, and you can taste it first. And let me know. Okay, so chemical energy. It's not just food, although food is an important one for humans. There's many types of chemical energies. You all study chemistry, so you know. For example, if you have an acid and a base, and you mix them together, you see lots of energy, lots of work being done. Or even if you just have an acid and you pour it onto something, you see the surface is damaged. So what's happened is a force is breaking down, like a hammer nearly, breaking down the surface. So the acid is doing this work. For food, of course, the energy is important for us because this is how we get our energy to do the work that we do. It's from food, which is just a chemical energy. Our body takes the energy from the food. Okay, so like a biological energy, yeah. So chemical energy, if you can write that down, please. Yeah, you got that? Chemical energy. So I think most of the energy, which is chemical for humans, is mostly just sugar. Or other things like sugars, I don't know, stuff like this. Okay, continue.
Yeah.
So the next type, radiant energy. Now, I don't know if you know this word. What do I mean by radiant?
Sunshine.
Yeah, this is like light, sunshine energy. Energy from the sun. Again, this is important, but on Earth, what thing most needs this energy on Earth? Plants, yeah. So plants get their energy in this form, radiant energy. Some plants get it in chemical form as well, but most plants get most of their energy, radiant energy. Yeah, okay, so if we can write this one down, radiant energy. Yeah, what's another word for radiant? What synonym could I use? Solar energy. Good, yeah. Solar energy. And in fact, on some of your calculators, not that one, this one is powered this way. Yeah. Okay, did you write that down? Yep. Next one now, nuclear energy. An important form of energy, especially for some countries. It can release a lot of energy. It can do a lot of work, this nuclear energy. We'll study this more in semester 2. Yeah. Okay, you got that? Continue? Yeah. Now this is something you might have done in chemistry. Ionization energy. Have you done ionization in chemistry?
Yeah.
Yeah, so what's ionization? To remove an electron. Yeah? So, if you want to, I suppose if you have an electron and it moves into an orbit here, you can get some energy. Or if you have an electron and you want to take it out of the orbit, you have to give it energy. So if you want this to pop out, you have to give it energy. This is called ionization energy. But likewise, if it pops in, then you can actually get some energy out. And again, we'll study this in semester 2. Or perhaps somebody knows how do we get the energy out? If the electron pops into an orbit here, some energy comes out, this ionization energy. What form is this energy actually? Does anyone know? No, okay, I'll tell you in semester 2 then. I won't ruin the surprise. Okay, so ionization energy, if we can write this down. Okay, you got that? Continue? Yeah? Next. Simple one, elastic energy. Now, this is an important energy in engineering because most materials are a little bit elastic. Like, even if you think about a big metal bridge, it still bends and compresses a little bit. You know, so like the wood in the window, that wood still compresses a little bit, and we actually still call this energy an elastic energy. Even though it's not elastic, it's wooden, we still describe it as an elastic energy. So a very important type of energy in engineering, because a lot of things are elastic, that they bend a little bit or, you know, curve a little bit or whatever. So elastic energy is the next type. Okay, you got that? Yeah. Okay, another type, gravitational energy. Now, if you think about this, here, can you see this little guy here? He is getting pulled, well, not he, it is being pulled to the sun. So just like the magnet, the sun is doing work. What is it doing? It's applying a force over this distance. So just like with the magnet, there's a gravitational energy. This has the ability to do work. It can pull things into it. So just like the magnet, gravitational energy. Yeah. Okay, continue. Right, next one. Heat energy. Again, another important form of energy for humans. Okay, got that one? Obvious one. Not so obvious here, but mechanical energy. Again, if you think about an old clock, you can turn the key in it, and as you're turning it, you're giving the clock the ability to do work. What work is the clock doing? Yeah, but precisely what's it doing? Like, describe visually what work can you see being done. That's it, yeah. So by turning the key, you're giving it the ability to move the hands, which is, in other words, the ability to apply a force to move the clock hands around. So mechanical energy. And again, although this seems old-fashioned, it's still an important form of energy, because if you think about cars and planes, you still need to think about this sort of mechanical energy, how the turning of the cogs and the wheels can do work. Okay, next one. Wave energy, energy that waves have. You can. What work is the wave doing? What work is this wave doing? If it has energy, it can do work. So what work is it doing? True, moving the water. Yep. But that's not so exciting. Give me some exciting work it can do. That's even more boring. Give me something exciting. Yeah? Doing what? That's it, very good. So, if you look at where the wave hits the coast, you can see the force. It actually breaks the coast. You can see the rocks falling into the ocean. Okay. Now this, in Ireland, is a very important form of energy, because if we can use this energy, it would really be very valuable in Ireland, because in the west of Ireland, has the third most wave energy in the world. So there's only two other places other than the west of Ireland that has more wave energy. So if you can take this energy from the wave, then you really have a lot of energy, because like I said, the west of Ireland's third most energetic waves in the world. So Ireland is trying to develop ways to take this energy from the waves. And if you've been to the west of Ireland, you can see how much force this wave hits against the west, because the west of Ireland is if you look at the map, it's very jagged. But if you look at the east of Ireland, it's more smooth. Okay, so wave energy will be an important one in Ireland. Kinetic energy. Does anybody know this energy? What's kinetic mean in here? Movement energy, yeah. Do you know, I suppose the difference, mechanical really nearly is a type of kinetic energy. If you get really technical, you could nearly say all forms of energy are kinetic, because it's usually because something is moving, you know. So when you look at physics in a more pure sense, if you know what I mean, and look at everything on like the right scale, then you might end up saying, well, then everything is just kinetic. Because even if you look at have you studied biology before? I think even if you look at chemical energy, the process of getting the energy from the food is actually kinetic as well, because it's just, you know, I don't know, sugars moving around and stuff like that happens. So anyways, you could actually say everything is nearly kinetic energy if you look at it at the right level. Okay, so kinetic is for movement, and the next one is potential. But by potential I mean situations like this. This rock has the ability to do work. What work can this do?
Or down.
Yeah, but what's the force? Yeah. Yeah, so the ability, the work that this rock can do is to break his head open by applying a force over a distance. So it can do work. Okay, so, and it'll be quite easy to make it do work. You just have to knock it over. So potential in this case means the ability to do work because it's at a height. Because it's at a height, it can do work. If this was on the ground, it couldn't do work. Because if you wanted to break his head open, you would have to lift it up and drop it on him. Okay? So that's potential energy. So there's the key types of energy. So next now we have our first rule for this lesson. The actual name of the lesson, conservation of energy. So, I'll say this twice. This is the most important rule in physics. And for those people who didn't hear me the first time, it's worth saying twice. This is the most important rule in physics. Most important. Conservation of energy. Energy cannot be created or destroyed. Instead, it just changes from one form into another form. Now, I said this is the most important rule in physics. And the reason it's the most important rule, in my opinion, is it's the only rule in physics which is always true in every area of physics, without exception. There is no part of physics where this rule is not true. It is true in mechanics, it's true in electricity, it's true in chemistry, it's true in biology. In every part of science, this rule is true. There's no exception to this rule. This is, I think, why it's the most important rule. Because with some rules, there are exceptions. Like, okay, this rule works 90% of the time here, but it doesn't work 10% of the time here. You know? But this is not the case for this rule. It is true everywhere in science. So that is why it's the most important rule. So what it says is you can't make energy, you can only change it. Example, here the energy is electrical. But when it changes from here to here, it's not destroyed, it just changes to a different form. So previously it was electrical and now it's what? What is the energy here now?
Light.
Well, yes, light. That's one. There's actually other types too. Heat, yeah. I can feel a lot of heat coming out of this. And what else?
That's very chemical.
There's a mechanical because there's things moving inside of my laptop now. What else? Yeah, actually my battery's charging up. So there's electrical energy in the battery now.
Potential.
Well, the potential didn't come from this. It came from me lifting it up and putting it on the table. So maybe not potential. A little bit of sound. Because you can hear sound coming from the projector. If you calculate the energy of the light, the heat, the sound, the mechanical, the battery, and add them together, it will equal how many joules came out of this. Yeah? Exactly. Exactly. Yes? Okay, did you write this down? Yeah? So, if I lift this up, what energy does it have now? Potential. And where did it get this from? What was the previous form? Yeah, so what form of energy was it previously? Yes, and before that? Not quite. So, I gave it kinetic by moving it. What energy was it before? It got the energy from my arm. So what energy was that? Chemical energy. And where did I get the chemical energy from? Well, I mean, I burnt calories. Well, calories, maybe one, perhaps. What was it before that? I know. Food, chemical. Yeah, it came from my food. So I had a sandwich for lunch. Okay, what energy is that? Chemical. Right, so let's say I had what did I have? I had bacon, lettuce and tomato. Right, so the bacon, that's food energy. Where did it get its energy from? From the pig, good. Where does the pig get its energy from? From the food, so let's say it eats hay or whatever. Where does the hay get its energy from? From the sun, yeah. You see, you can trace it backwards. But then it starts getting complicated. So the sun, where did it get its energy from?
From nuclear.
From nuclear, but where did that energy come from?
You should ask Hawking.
I should ask Stephen Hawking, yes, perhaps, yeah. So the point I want to make here is the conservation of energy says the energy stays the same. But what I think is interesting about this is it never says where the energy came from to begin with. It can't. It only says it stays the same. But it's not telling me where it came from to begin with. That's where it gets complicated. Huh? Yeah, but where did the sun get its energy from? And where did that get its energy from?
Oh.
You see what I'm saying? So, yeah.
The chance of this rule is not true.
Yes, there's a chance, of course. Yeah. No, but I'm just saying, as important as this rule is, just like every rule in science, it has its limitations. So this is great for saying that the energy tomorrow will equal the energy today. But it cannot tell me where energy came from. Do you know what I mean? So I'm just trying to really make a point that every rule, even a great rule that works everywhere, has its limitations. That there's always times when you can and can't use it. In this case, I can't use it if I go back far enough. If this rule cannot tell me where the energy to begin with came from. We'll have to ask Stephen Hawking on that one, okay? Right.
So that means the whole world has the same amount of energy?
Well, there's two things happening. No, roughly, but you got to remember, there's energy always coming in from the sun. And there's also energy leaving because the heat kind of reflects off. I don't know. Well, actually, I do know. At the moment, which is greater, the energy coming in or the energy coming out of the Earth? Which is bigger, energy coming in or energy going out of the Earth? Not the same, actually. Oh, interesting. We have a different opinion.
Or coming in because the ice is melting.
Correct, very good. The energy coming in is greater than going out because it's being trapped. Do you know what I mean? So the energy comes in from the sun, but not as much as going out. So, getting a little warmer, And this will continue to happen until the energy going out will equal the energy going in. But at that point it'll be, nice and toasty and, it could have all drowned at that point. So, okay. I'll let you try these for a couple of minutes and then we'll finish. In just about 5 minutes. These questions are very simple. They're thinking questions. I want you to think about things. Yeah?